All right, everybody, we're back again for this video that covers information from section 5.10 from AP Calculus, Introduction to Optimization Problems. Okay, so in this section we're going to introduce you to optimization problems. We'll go through a few examples. In the next lesson, section 5.11, we'll do some more talking about solving optimization problem. It's kind of a two-part thing. So first of all, what's optimization? Well, we're finding the optimal value. What's an optimal value? An optimal value is the best situation that we can have for a specific context, which, depending on what we're looking for, it might be a maximum or it might be a minimum. You know, businesses want to minimize their expenses or maximize their profit, or you might want to figure out the least amount of money that it's going to take you to produce a given output. Or you might want to figure out the quickest way that you can get somewhere. These are all examples of optimization type problems, where we're trying to find a maximum, something that produces a maximum or minimum value for, the pertinent function. The whole idea is when we're solving optimization problems, we're going to follow the same typical process. The only variations that we're going to see is in how we build the model. So here's the process. 6 steps set up here. First off, draw a picture, if it's applicable, and identify known and unknown quantities in the process. Okay, for some of these, we won't have to draw a picture because it doesn't make sense to draw a picture. You'll see that with the first example. But if you're in a situation where a picture is helpful, it's a good idea to go ahead and set that out as your first step. Write an equation for the quantity that you're trying to optimize, the quantity that you're trying to find either the maximum or minimum value of. Use the constraints that are given to find relationships between the variables. Usually in every optimization problem, there's some kind of constraint that ties maybe multiple variables together and limits them in the process. Step 4, rewrite your equation in terms of one variable. So we're going to combine the equation that we have from step 2 with the relationships that we get from step 3 and try to write it all in terms of one variable. Then we're going to take the derivative and identify the critical values. And then we'll use either the candidates test or the first derivative test with a sign chart to help us identify the extrema in the situation. And then lastly, we will interpret the answer in context. So in this video, we're just going to go through a couple of fairly simple, relatively simple optimization problems using this process so that we kind of get an idea of what it is. Now, what's really hard in optimization for us really is developing this model. Once we've got the model, it's a matter of take the derivative, figure out where it's 0 or undefined, analyze the situation, find the maximum or minimum, and then apply that to our problem-solving context. Those are all things that we have already done in this course. All right, so let's get it started here. Example number 1, we're going to find two numbers whose sum is 45 and whose product is as large as possible. It doesn't make any sense for us to draw a picture in this situation. I mean, how can you draw a picture of two numbers whose sum is 45? So that's kind of silly in this context. So let's go through the process. Step 2, write an equation for the quantity that we want to... So we'll do step 2. Sorry, my stylus didn't work there for a second. We're going to find two numbers whose sum is 45 and whose product is as large as possible. So step 2, we're going to write an equation for the quantity that we want to optimize. We want to optimize the product. We want the product to be as large as possible. So we're optimizing the product of these two numbers. I'm going to call the product, I'm going to use capital N for that number, and I'm going to call the two numbers X and Y. I know, pretty bland, but it is what it is. So there's our equation for the quantity we want to optimize. We're going to try and optimize N in this context, the product of those two numbers. Then we talk next about the constraints, step 3. we're told that the sum of these numbers is 45. So that's the constraint on x and y, which means that the sum means plus, so x plus y has to be equal to 45. All right, so that's the constraint that we have on our variable. Now we're going to combine these two equations, the one that we wrote in 2 and 3, and we're going to do that in order to rewrite the equation in terms of one variable. So what I'm going to do is I'm going to go ahead and solve this constraint for one of the variables, and then I'm going to substitute that in step 4 into my expression for n. So we're going to replace y with 45 minus x, and therefore my number that I'm trying to optimize is 45x minus x squared. There's my equation in terms of one variable. All right, and then I move on to step 5. Let's find the critical points. So I take the derivative of n, gives me 45 minus 2x, and I set that equal to 0. And I find that that's 0 at x equals 22.5. That's the only critical point that we have in this situation, and we don't have any endpoints. I mean, I could have a negative number and a positive number. Of course, then my product's going to be negative, so I know that realistically I'm looking for positive values here. Once I find that this is my only critical point on the interval, there's really two possibilities that can occur. Either this is where the optimal value is going to be for me, or there is no optimal value. That does happen sometimes. So I do my analysis of my sine chart here. Let's see, if I put 30 into the derivative for x, this is negative, and if I put 20 in, it's positive. That means that this is a relative maximum, and it is the only extreme value in the problem. So this verifies that it's a max. And now I'm going to interpret my answer. So x is equal to 22.5, which means that y is equal to 22.5 as well. And so, step 6, the largest product of two numbers that add up to 45 is produced by 22.5 times 22.5. Okay, now notice that the problem doesn't ask me what the product is, so I really just need to identify the two numbers, and there we go. I'm done. Let's go on to our second example here. An open top box, good old open top boxes, is to be made by cutting congruent squares of side length x from the corners of a 30 by 45 inch sheet of cardboard and bending up the sides. How large should the squares be to make a box of maximum volume? What's the resulting maximum volume? So, step 1, draw a picture. So here's my box. Or my piece of cardboard. And we're cutting out squares with side lengths x from each of the corners. And then we're bending up the sides. So we're cutting out these squares that are solid blocks, and we're bending up the box along the dashed lines. Okay? This is 30 inches, this is 45 inches along the top. So, what are we trying to maximize? We're trying to find a box of maximum volume. So the volume is equal to the length times the width times the height of the box. Okay? Now we don't have, a written equation for the constraints like we did last time. What we need to figure out here is what the length, width, and height are in terms of our picture. And when I bend these sides up, one side is 45 minus these two distances, so it's the quantity 45 minus 2x. The other side is the quantity 30 minus 2x, and then the depth of our box is just going to be x. So there's our expression for volume. I'm going to go ahead and simplify that equation and turn it into something that's nice for me to work with. I'm going to multiply all these things out, and when I do that, I get that the volume is 4x cubed minus 150x squared plus 1,350x. So now I have the volume that I'm trying to maximize written as an expression of x. So I'm going to go ahead and move on to step 5, finding my critical values. And so I take the derivative of this function. There's my derivative. And I'm going to solve this for x. Pardon me. I'm going to set this equal to 0, and then I'm going to solve for x to find the critical points. Now notice, there are limitations on the values that x can have. First off, x has to be positive. And also, x has to be smaller than, I should use just a strictly less than. X has to be less than 15, because if it's 15 or larger, we're cutting out the entire chunk of cardboard that we've got nothing to bend up. So x has to be between those values. So we solve this function. Punch it up in your calculator, use a quadratic formula, however you want to do it. It doesn't factor nicely or anything like this. I've already solved it. It's x equals 5.886 or x equals 19.114. This one we can exclude because it is not in the interval from 0 to 15. Okay. Actually, let's make that open on both ends, because x can't be 0 either. Duh, we've got to cut a block out. Sorry. All right. And so now I make my sign chart. And I substitute a number bigger than 5.886 into my derivative. I'll do 10. That's 1,200 minus 3,000. That's going to be negative. And I put 5 in here. Let's see, that's 300 minus 750. So that's positive. So again, looking at my sign chart, this is a max. And so now all I need to do is finish up with step 6. You should cut out squares with side length 5.886, and my units are inches. Okay, that answers how large should the squares be to make a box of maximum volume. The resulting maximum volume if I substitute this value back into the volume equation, it's going to give me a volume of 3,565.032 cubic inches. Please note, this is a rounded value. When I calculated this value, I used the calculated value from my calculator. Unrounded is what I substituted back into the volume equation in order to get an accurate final answer. Do not, absolutely do not put your rounded value in for your final volume calculation. I know it's irritating to keep all those digits when you're calculating, but if we want our final answer for the volume to be accurate to 3 decimal places, it's something we need to do. All right, we're done with this video. You're going to get some practice writing up models for optimization problems, and then in the next lesson we're going to talk more about how to solve them. Okay, have a great rest of your day, everybody, and we'll see you next time.